All right, last time I think we stopped with around precession. Remember, precession is um, the wobbling that the Earth's axis does. It's a very very slow wobble, taking 26,000 years to complete one cycle, and it's a very slight effect. Um, but okay, let's keep moving here. The next one. All right, now what we're going to do is talk about keeping time and oh, I think I covered this already. This is latitude and longitude. I think I covered all this. All right. Sorry, I thought I was in the right place. All right, so measuring time. Um, all right, so of course humans have tried to, measure time, and the idea of a day, for example, is a seemingly simple thing, but it turns out it's a little more complicated than that. And the other thing is, I mean, if you just think about human cultures around the world, they've tried to keep, try to keep time at various ways. Some cultures have used the moon, others have used the sun and the position of the sun with respect to the stars. But the problem is, until we had, very recently in human history, electronic timing devices, it was very, very, very difficult to keep time, because it's not constant. Like, for example, the day is not 24 hours long. It would be really nice if it was, but it's a little shorter than that, and that causes a lot of problems trying to keep time. All right, so let's move on here. Here's our first situation. For example, the time it takes the Earth to rotate all the way around. All right, so what exactly do we mean by that? For example, if you looked at where the sun was, and you said, okay, when the sun is the highest in the sky, of course, that's noon. We discussed that earlier, and you would think that one day, 24 hours later, you'd look from your position on the Earth, and the sun would be, exactly the highest. But the problem is, the Earth is, of course, moving around the sun, the revolution around the sun, and so it's moved, and so there is this additional time that has to take place, because the Earth has moved, and so for the sun to be the highest in the sky, there's an additional rotation, a little bit more in the Earth's rotation. All right, so. What we call a mean solar day, or kind of like the average time, is the 24 hours. Okay, so that's also known as a mean solar day. And there's also what's called a sidereal day. We'll get to that in just a second. Oh, here it is. Okay, so a sidereal day is the time it takes the Earth to rotate with respect to the stars. Sidereal means star. And so the time it takes the Earth to rotate, if you marked a location in the sky, for example, I mean, even people a long time ago knew about this. If you mark a location in the sky, and then you wait for example, for a star to pass that location again. You take a long straight stick or something like that, and you aim it at that star at a particular, let's say when the star is making its arc in the sky and it reaches the highest point, how long does it take for that star to come back to that exact position? And that's what we call a sidereal day. Of course, this is where the problem lies. It's not exactly 24 hours. Okay, so so the sidereal day is 23 hours, 56 minutes, and roughly 4 seconds. Of course, that changes as well, slightly, because as the Earth goes around the sun, it's speeding up when it gets closer to the sun, speeding up a little bit, and then as it's a little further from the sun, it slows down. So this is not constant, unfortunately. This thing called the equation of time. Let's take a look at the picture here. What happens with the equation of time if you and ancient peoples around the world knew about this, as a matter of fact. If you were to make a little hole in the roof of some building and just mark the location of the sun on the floor, like as the sunlight comes in, let's say at noon, for example. So you'd have to, somebody be standing outside, and they would say, okay, now's the point when the sun is the highest in the sky. Mark the location of the sun. And so what happens with that is it makes your book has a nice picture of this. It makes a figure eight, but it's a lopsided figure eight, where the smaller circle is during the winter time in your hemisphere, and the longer part of the figure eight is during the summertime. Hold on. Let's see. No, let's see. The longer figure eight would be in the winter time, because the sun is lower in the sky, and the shorter part of the figure eight is in the summertime, right? Because the sun is higher in the sky. All right. So anyhow, that's also known as the equation of time. And all right, let's move on from that. So of course, to keep time, we have these. If you take 360 degrees, the full, all the way around on a circle, and you divide it into 24, you get 15 degree zones. And what we've done, of course, all the way around the world, not just the United States, but all the way around the world, we mark these zones, and we call those time zones, of course. We live in the eastern, of course, in South Carolina, as with the entire east coast of the United States, we live in the eastern time zone. And these things are not straight lines at all. They adjust these for the convenience of different locations. For example, you can see here that Tennessee, for example, is almost cut in half between the eastern time zone and the central time zone. And so, what are some consequences of this? If you ever, of course, if you fly to the west coast, for example, from the east coast, you have to, when you arrive, you would have to turn your clock back 3 hours, right? Because it's, you have the eastern time zone, there's the central, there's the mountain time zone, and then the Pacific time zone. Okay, and the opposite is true if you're flying from west to east. All right, and then there's through England, through England, there is the prime meridian, right? And then 180 degrees from that is what they call the international date line, right? And if you're traveling across the international date line, you either lose a day or you gain a day. And so what that amounts to, generally what you do is, if you're like on a ship, for example, you would wait until midnight, and then midnight, if you're losing a day, you would go to the day, you would go one day, let's say the day is the 20th, and then what would happen is at midnight you wouldn't go to the 21st, you'd go to the 22nd because you lost a day. And then the opposite would be true. If you gain a day, then you would let's say it's the 20th, and then when it would normally be the midnight, it would turn into the 21st. You just switch it back to the 20th again. All right, and it's a little strange. I've done this when I was in the Navy and crossing the international date line. You don't really even notice it because nothing's actually changed. It's just keeping coordinated time throughout the entire world. Okay, let's move on. Okay, so the time it takes between two equinoxes, for example, from the spring to spring, is 365 and a little less than a quarter of a day. Those are mean solar days. And for the sidereal year, the interval between two consecutive alignments of the Earth and the Sun, with respect to the stars, it's a little different. It's a little different, of course, than the tropical year, and it's a little about 20 minutes longer. And this is what comes in when you talk about the Julian calendar that goes back to the Roman times, and then in medieval times there's the Gregorian calendar to try to adjust the calendar for these, the fact that the rotation of the Earth and the movement of the Earth around the Sun doesn't match the time it takes the Earth to just simply revolve around its axis. All right, and here is the sidereal month, and this is for example for the moon, right? For the time it takes the moon to rotate all the way around, and it does actually rotate on its axis, is 27 1/3 day, as it says right here. The synodic month is the time interval between two consecutive phases. For example, the time it takes to go from new moon to new moon. That would be a synodic month. And that's important because there's still cultures, for example, Islam, and certain Jewish holidays follow the phases of the moon. And so keeping track of the phases of the moon and what these and actually how this varies from like the Gregorian calendar makes things very interesting. All right, let's see. I'm going to get into this in the next video, I believe. So I'm going to stop here.